I want to discuss the conservation of momentum. What this means, for example, is the momentum of the cue ball just before the impact is equal to the amount of momentum that all the balls have together just after the impact. The momentum before is equal to what it is after. That's what we mean by the conservation of momentum. So we want to understand a couple things, a few things. First, why is it true? Under what conditions is it true? And then how do we use it like in problems, in examples? So we're looking at the conservation of momentum now. Conservation of momentum, the law of conservation of momentum, it says that as long as there are no external forces, so we say in an isolated system, isolated system means zero external forces. So we're only considering the forces between the impacting things, like we're ignoring any other like friction, for example, that might affect how they move. In an isolated system, the total momentum of all the parts before the interaction is the same as what it is afterwards. The total momentum before interacting is equal to what it is after. So we call it conservation law, when something is before an interaction is the same as what it is after the interaction occurs. Let's understand why this would happen. Let's just take a simplified example of like one ball hitting another one. So this ball comes in at a high speed, and it's going to strike a ball that's sitting at rest. A billiards type situation. This ball comes in with some momentum. Now, when they hit each other, remember that during an interaction, the forces they feel are actually identical. It's just that this one feels a force of impact back to the left. This one feels an equal strength force, but directed to the right. So they both feel the same strength of force, and also the time is the same. In other words, if the left ball feels the force for a split second, the right ball feels the same force for the exact same amount of time. Okay? In other words, both objects experience an equal but opposite force for equal amounts of time, and therefore, if you compare ball 1 and ball 2, they feel equal but opposite impulses. Same force, same time. Now, if they both experience the same impulse, that means the change in momentum they get is the same. In other words, ball number 1, that ball is going to slow down. It's going to lose a little bit of momentum. But ball number 2 is going to gain exactly the same amount. You see? So the total amount actually stays the same. Number 1 will lose a little bit. It's a little bit of change in momentum that it'll have in the impact. But ball number 2 will then gain exactly the same amount. So it's like ball number 1 loses $5, but ball number 2 gets the same $5. Overall, it's just an exchange of momentum. So that's how the law of conservation works. One object loses it, and the other object gets this exact same amount. Here's an example. A cannon, before it's fired, has 0 momentum. I can tell because although it has a big mass, it has no velocity yet. So 0 momentum. Afterwards, the cannon also has 0 momentum. It has, in fact, 0 momentum before and after. It's fired. How does that make sense? Because after it's firing, the projectile's flying out. Also, remember the cannon recoils backwards, and that's really the secret to it. The ball gets some momentum. The cannon itself must recoil back with exactly the same momentum. But does that make sense? Doesn't the ball go flying out at a super high speed? Sure it does. It has a small mass, relatively speaking, and therefore has a giant velocity. Versus the cannon itself has a tremendous amount of mass, big mass, it recoils at a lower speed. The momentum of both parts is the same. It's just one of them is positive, the other one's negative, and therefore it stays zero. Let's now apply momentum conservation to collisions. For all collisions in the absence of external forces, the total amount of momentum before the collision is actually equal to what it is after. The example I gave was in billiards. The momentum of the cue ball is equal to the amount of momentum that's in all the other balls after the break occurs. Now, the part about no external forces is important because, of course, a moment later, the balls slow down because the friction as they roll slows them down a bit. Also, they hit the walls of the table, and that's an external force that makes them change their direction. So it's not that the momentum is conserved forever. It's only conserved as long as the external forces are negligible, can be ignored. Okay, there are different categories of collisions. First category of collisions are elastic collisions. Elastic collisions are perfectly bouncy. They're bouncy collisions. Now, we talked about when one thing bounces off the floor, it gives a greater force compared to the sad ball. Here, I'm not comparing happy versus sad. I'm just saying, suppose it's a perfectly bouncy collision. And when that occurs, the momentum stays the same during the bounce. So, for example, during an elastic collision, example being billiards, one ball comes in, they just trade velocities. Notice how the momentum, this one has some momentum beforehand, this one has zero. The total amount of momentum is all in this ball here. Then after the impact, the momentum just gets traded. The green ball loses its momentum, and the yellow ball gains the exact same amount. The before amount of momentum is the same as what it is after the impact. That's how we can see evidence for momentum conservation during the elastic collision. Elastic collisions can also happen in a head-on collision, where both objects are moving towards each other. Then let's look what happens. This one has a momentum. This one has two. It also has momentum, but it's negative. So the total amount of momentum beforehand is actually zero. Plus 10 minus 10 adds up to zero. After the impact, if the collision is elastic, then this one rebounds with minus p, and this one has plus p instead. And notice that, again, the total amount stays the same. It's still zero. These are just two simple illustrations of the conservation of momentum. It's zero before, and it's still zero after. Now, these elastic ones, they're very common. Bouncy things hitting off each other, they're elastic collisions, like billiards. However, they're not so good for just solving problems because they're complicated. They have two moving parts before and afterwards. So instead, we typically will look in detail at inelastic collisions, where the objects stick together. Instead of rebounding off each other, they stick like two train cars coupling together. Same rule applies. As long as there's no external forces that slow them down or make them bounce or something, then the momentum is conserved. Whatever it is before is equal to what it is afterwards. So let's look at this collision of the train cars. We have two equal mass cars I don't know what their mass is. I know it's huge, but I don't know what the mass is. All I know is one of them's coming in at speed of 10 and the other one's at rest. Then they're going to collide together and couple and make an inelastic collision. Okay, so the question is, what is going to be the speed? Find the final speed. Now let's think about this. Before the impact, I've got one car moving at a speed of 10 and the other one's at rest. No speed at all. Now, after the impact, they're both moving together. In other words, the total mass that's now in motion is 2m. So let's think about this. The moving mass beforehand is just m, but afterwards it's 2m. Can you see that if you double the mass, you have to cut the speed in half to keep the momentum the same? Remember, momentum is mass times velocity. So if you double the mass, you'll have to have the speed to keep the same momentum. And for that reason, the speed after the impact is only half as big. Double the mass, now it's 2m that's moving, and 2m would have to have a speed of only 5 to keep the same momentum. Let me write it out so that is maybe more clear. Beforehand, the momentum, the total momentum, is m times 10, mv. It has to be the same as what it is after the impact, but after it's 2m. The mass is 2m, multiplied by the speed afterwards, which is 5. You see, that way it's the same. 10m equals 10m. Same, before and after. That's how momentum conservation works. Let's have some more examples of these inelastic collisions. A big fish, 5 kilos, eats a little fish, 1 kilo. The big fish beforehand has a velocity of 1. The little one is not moving, 0. It's at rest. Let's find the velocity after the impact. The way we do it is you find the momentum beforehand. The momentum beforehand will be big M, that's 5 kilograms, multiplied by its velocity, which is 1. But you see, it has to be the same momentum before as it is after the impact. After the impact, the mass is 6, 5 plus 1. It's moving at an unknown speed. The problem is to find what that speed is, which we do using algebra. The equation for it is now 5 equals 6v. In other words, the velocity has to equal 5 over 6. 5/6 of a meter per second. Notice how the big fish does slow down. It's now less than 1 meter per second. It doesn't drop by half because now the little fish isn't as massive. Compare that to the train cars. When one train car hits another one of equal mass and they stick, then the velocity drops by half. But if it hits something which is smaller in mass, then the final speed is not reduced as much. Let's repeat that example, but suppose they're now both moving. This one is 5 kilograms. This one is still 1 kilogram. But now the big fish is moving at 1 and the little one is also heading towards like a head-on collision. They're moving at equal speeds towards each other. Pause it and try to work out the final velocity before I work it out. Okay, the process is the same. I have to write down the momentum before the impact. Big fish has a mass of 5, a velocity of 1. But be careful, I got to be careful about the signs now. It's moving to the right, so its velocity is plus 1. The little fish, I have to add its momentum in. Its mass is 1 multiplied by its velocity, but its velocity is -1. It's moving to the left. So now you see the momentum beforehand is 5 minus 1, and that's equal to 4. Okay, so now I know the amount of momentum before the impact. But that's exactly equal to the amount of momentum after the impact. After the impact, the mass is 6, moving at an unknown speed. I should say unknown velocity. Okay, so now the velocity, I solve. 4 equals 6v. I divide by 6 and find that v is 4 over 6. In other words, 2/3 of a meter per second. Let's compare that to the previous example. In the previous case, the speed was higher. And that should make sense because this fish was at rest, the small one was at rest. In the next case, this fish was actually running into it. So that would actually make sense that it gives a final speed which is smaller during like a head-on collision, which actually slows down the big fish more. So when we meet in our Zoom lecture, I'll work through a number more of these examples so that you have more practice. These are again like guaranteed type of test questions of the problem solving type.